Okay, let's take a look at this problem. I like this one a lot. These are two blocks that are stacked and they're on a horizontal surface. The interface between the bottom block and the surface beneath it is a frictionless interface, but there is friction at the interface between the two blocks. So there's friction at this interface here, and we're given the coefficient of that interface as well. And what we're told is that there's some applied force F prime, right? And now just imagine this situation, okay? So there's some applied force F prime, and the outcome here is that the acceleration of block B is twice that of block A. So you can kind of imagine that. Just think that block A and block B don't travel together, so the interface isn't static, right? There's kinetic friction here, so there's sliding at the interface. But both of the blocks are set in motion when there's an applied force just to the top block. Okay, so you got to kind of wrap your head around that. And then we're told this really important piece here about the acceleration proportion, that the acceleration of block B will be double that of block A. Okay, so that's something that we're going to have to write in terms of, uh, we can just write that simply in an algebraic equation. So cool. Let's think about how we want to approach this. We're going to approach this using energy analysis. This is a problem that is also interesting, and of course, you're able to approach it using force analysis. So you can work it using energy analysis, and you can always check your answer using force analysis. So I just want to remind us with energy analysis, we're looking at our equation. The change in overall mechanical energy is equal to the work done by our non-conservative forces. And the definition of work here, we're looking at the scalar product between force and displacement, remembering that works are done by forces. Okay, so a good place to start here is free body diagrams of these two blocks. We can't really do much else until we have figured out what are the forces acting. We know that for the right-hand side of the situation, we need to know what those non-conservative works are. And then, the left side of the equation, just considering the change in mechanical energy, that's fairly simple for this case. There's no springs, so there's no elastic or spring potential here. Um, there's no incline or any kind of change in elevation for either of the two blocks. So we're not even considering gravitational potential energy here. So really the focus or what's interesting about this problem is the works here. So let's look at the free body diagram for block A and the free body diagram for block B and go from there. So go ahead and start, if you haven't already done that, drawing out your free body diagrams. We've done quite a bit of problems in our force analysis section on with stacked blocks. I think these are really good applications of theory. So you might want to reflect back on some of those that we've done. So if I'm looking at block A, we'll start with block A here. I'm going to look at what's in contact with the block, right? That's my forces have to come from contact, except for weight. That's the only invisible force I get. So what's in contact with the block? Well, I've got the surface beneath it in contact with it. That surface is exerting a normal force. And we're told that that interface is frictionless, so that surface is not exerting a frictional force. Surfaces can only exert frictional forces and normal forces, so I know I'm done with that contact point at the bottom of the 3M block. There's also a contact point at the top of the 3M block where it's in contact with the 2M block. At that surface, I'm going to have both a normal force, which is pointing down, and I'll call that NAB, the normal force at the interface between blocks A and B. And then there's also a frictional force that's applied. At that interface, we are given the coefficient of kinetic friction. So here you have to ask yourself, all right, well, what is the direction of that frictional force? Well, this is meant to look like an N. And then I'll go ahead and put in the weight of this block as well, just to kind of get that, because that's also going to be directed in the same direction as that other normal force. So the only thing we need to figure out then is friction. So what I know here is I know that this bottom block will be accelerating to the right. I know that the bottom block will be accelerating to the right. Sure, its acceleration is going to have half the value of the top block, right? But it's still accelerating to the right. So the force that's responsible for that acceleration is the kinetic frictional force there on that block. Okay, that might be easier to see maybe if you can, if it's simpler for you to think about it as in terms of a third law pair. Let's go over to the um, block B now and see and write the forces on that. So for block B, what do I have going on? It's being contacted again by the block beneath it, right? The 2M and 3M blocks, blocks A and B are in contact. So underneath it, what's going on with block B? Well, there's a normal force upward. This is normal force AB, the same one that's directed downward on block A. Those are part of a third law pair. And we have, of course, the weight of the 2M block. And of course, we have the applied force that that's what we're trying to find in this problem, right? We have this applied force F prime. And on this block, it might be more straightforward to see that, here we have the kinetic friction that's impeding. We can think of it in this traditional way as impeding our progress, right? Because kind of dragging that 2M block along the surface of the 3M block, and there is friction at the interface. The friction is opposing the motion. So that might be a little bit more intuitive for you. Looking at the free body diagram for A might be less intuitive for you, but I also really wanted to give you a scenario where the force of kinetic friction does positive work, because I encounter students that don't think that's possible, and it totally is. And this is an example of how it can be possible. So my displacements, I'm going to again kind of float those around. I have my displacements here. And they're both to the right. Again, this is fairly straightforward directionally here, but it allows you to see for block A that kinetic frictional force does positive work, and for block B, the force of kinetic friction does negative work. Kind of interesting there. So you can see some force pairs. We could see that this normal force here, of course, is part of a third law force pair, and this force of kinetic friction is also part of a third law force pair. Kind of cool. All right, so let's move along with what we're doing here. We can throw a sign convention on this. Remember that really what's important, because we're not using force analysis, right? We're using energy analysis, is the relative direction of force and displacement. That's what we keep our eye on here. So for as far as analysis goes, I don't know. I'll start with block A, doing my energy analysis here. And what I can see here is that a way to think about this is the change in mechanical energy for A equals the sum of the non-conservative works for block A. Sure. And what that can look like if we flesh that out in a little more detail is energy final for block A minus energy initial for block A is equal to, now look at block A, which of the works is going to be the work that's contributing to our non-conservative work. So our non-conservative forces on A are basically the two normal forces and the frictional force, right? Weight is a conservative force, so we don't consider that there. The two normal forces on the free body diagram for block A, they're both orthogonal or perpendicular to the direction of displacement. So they're not going to do any work. The only non-conservative force that does work for block A is the force of kinetic friction. So I know now that this is really going to be equal to the work done by friction on A. So let me go ahead and write this out. The final energy for A, well, that's just going to be kinetic energy. It's set in motion, right? 1/2 the mass of block A we're given is 3m. And I'm going to just call this V sub A. I don't know what that speed is there. Initially, let's say the system was at rest. And the work done by friction is going to be my frictional force dotted in with my displacement for block A. I'm calling that S. Okay, great. So I'm going to call the displacement for block A S, and then I don't know if you noticed it when we were doing the free body diagrams, but I'm calling the displacement for block B S prime. So notice they're not moving together, right? These blocks are not stuck together. They have different accelerations. They're going to have different displacements as well. So we need to keep track of that in our notation. So what is this going to turn out to be? 3 halves mv sub A squared is going to be equal to the force of kinetic friction multiplied by displacement multiplied by cosine of 0, which is just equal to 1. So that will then be equal to mu k times, let's see, now we have to figure out which normal force are we talking about here. So this coefficient of friction applies at the interface between the two blocks, and that's where the normal force, NAB applies. So that's the normal force I need to put in there. You always got to pause for a moment when you have more than one normal force and make sure that you're associating the normal force that actually goes with the coefficient of friction. So I could put here on the physical diagram on top, normal force AB, multiplied by the displacement, which I'm calling S. Okay, and if I go to my free body diagram for block A here, I can do a, actually, no, I'm going to go to my free body diagram for B, and I'm going to do a little analysis to figure out, to simply be able to express what the normal force AB is equal to. And if I look at my free body diagram for B, I see that I have no acceleration in the vertical, so I can gather there that this normal force NAB is equal to 2 mg. So that'll simplify this a little bit more. It's equal to mu k times 2 mg times S. All right, so that is, I'm going to stop there. That's an energy equation for block A, right? So I rendered this equation. One thing I want to pause for a second. I don't want to forget that we can render an equation based on this statement in the problem right here, that the acceleration of B will be double that of A. So acceleration of block B equals 2 times the acceleration of block A. So this is also an equation right here. Now, I tend to box my equations because I like to be able to count how many independent equations I have and make sure I have enough to the same number or more as my unknowns, so that I'm going to be ready to go algebraically. Okay, so that's block A analysis. Let's do our block B analysis, the energy analysis here. So what this is about, right, is that the change in energy for block B is equal to the sum of the non-conservative works on block B. So what do I have there? Finally, block B has kinetic energy, so that's 1/2 2m v sub B. Remember, their speeds are not going to be the same here. -0, initially nothing, we're at rest. And now I have to think about the forces that do work, non-conservative forces that do work on block B. So I can see that my normal force isn't going to do any work. It's at 90 degrees to the displacement. But I do have two forces that do have components, or actually in this case, completely lie along the same line as my displacement. And that is the frictional force and the applied force there. So this is going to be, I'm going to have two works here. One is going to be that F prime dotted in with S prime. I'm putting hats over here because I'm actually writing this in terms of the scalar product, plus now the scalar product of the kinetic friction dotted in with the displacement here. Again, different displacements, right? Okay, so what is this going to look like if we simplify this? MVB squared is equal to F prime. Now look at F prime. It's along the same line as the displacement. It's in the same direction. So what do I get there? I get F prime times S prime times cosine 0 for that case there, right? Plus, now my frictional force, displacement, and cosine 180 degrees between those two. All right. So what I end up getting for my MVB squared here is F prime S prime, cosine 0 is equal to 1, minus negative sign because cosine 180 is equal to negative 1, right? Mu k times 2mg S prime. Okay, so this is another equation. So I have three equations now, but if I pause and I look at like what are my unknowns here, um, I think I still have too many unknowns, right? So what are my unknowns? I have the F prime, S, and S prime, VA, and VB still here. Okay, um, so I need to keep going. I need to keep generating more equations, right? So let's do that. What else can I generate though? I've done my energy analysis, right? But what else can I generate? Well, I can also use some kinematics here. Now, we're told that this acceleration of B is twice the acceleration of A. Okay, so maybe I can come up with something that can relate my displacements and accelerations. That's kind of what I need here. And it's going to take some kinematic skills to do that. So let's try and do that. So here, this is our kinematics again. Remember that the reason we're doing this is we're given a relationship between the accelerations, and we need to establish some kind of relationship between the velocities and the displacements, right? And we know those things must all be connected because of kinematics, right? Because of what we know there. So let's see if we can define what those relationships are. There's block A and block B. So for block A, what I'm going to use here, I don't even want to mess around with time at all. I'm interested in, I think the most efficient equation here to use would be velocity as a function of position. Velocity is a function of position. So that general equation is, remember, v squared equals v naught squared plus 2a x minus x naught. It's one of our three kinematics equations, and it's a super useful one for a situation like this, where these are the quantities that we're actually interested in. So what would this look like? This would look like VA, right? My final velocity for A is equal to initial velocity in A is 0 plus 2A sub A, the acceleration of A, and the displacement for block A, we're calling that S. Okay, if I look at block B, VB squared equals, again, 0 plus 2A sub B. Now this is the acceleration for B, and the displacement for block B is S prime. Okay, so I've got some kind of relationship here. And then I want to sub in the fact that I know, remember that we were also given in the problem statement that um, the acceleration of B is equal to 2 times the acceleration of A. I'll write this down. This was given to us in the problem statement. So I think about that as like my first equation sometimes. So knowing that, then what I can find here is I can say that, well, VA equals 2, oh no, I'm subbing in Oh, no, I'm subbing in. Okay, so subbing in for, if I want it all to be in terms of B, then I'm sorry, then I'm going to write this like this: A B over 2. Yeah. So 2 times AB over 2 times S. So this gives me VA squared equals AB times S. Okay. And what did I get here? I get VB squared, just getting rid of the 0 basically, to AB S prime. Okay. Cool. So you're wondering, like, why is this cool? What do we do with these? Well, they're just more equations, right? That we can all use together. So this, from here on out, this your life is about algebra. So a way I could see this is that the equations that I've got an equation. Um, I've got this one here. I've got my energy equations, 2 and 3, and I've got 4 and 5. Those two equations there. And at this point, you kind of have to just go to town and start using those equations and keeping your eye on the ball that what you're trying to solve for is f prime. And you just use your favorite. I use substitution if you look at the written solutions, but like you just do, again, algebra's personal, do your own thing. So what we end up getting for f prime is fairly elegant: 14 mg mu k over 3 as our final expression. And that's that problem.